Right. So, hey guys, as you might be aware already that I had posted this blog on Medium and uh, related the LinkedIn post, but there was no video recording or video explanation of what this project was. So here in this video, I'm going to explain what I had done in this project and also the part two of this project, which is basically training those variants and checking if that variant is actually giving the correct accuracy even after whatever compression we did on the model. So let's get started. Yeah, so let's go back to the blog first. So what usually happens is in these LLMs or large language models, uh, with growing usage of these models, the context length of these models is also increasing, and how much these models have to remember with all of these heavy applications like agentic or code based analysis or even suggesting or creating something from scratch, remembering what they have done already is very important. So what happens is, in order to save time, we have incorporated something called as KV cache, where we trade the speed for memory. So, or rather, we trade memory for speed. So, we assume that we have enough memory to store all of the things that the model has done already or has processed already, and then go forward and start doing the current work that has been assigned to that LLM. So, even if the model size is itself small, the context or the work that it has done is so large that you end up spending more memory to store all of that context rather than hosting the model itself, right? So that is basically the current bottleneck that LLMs are facing. So it's not just massive GPU clusters and training it on trillion tokens, right? Once you have trained the model, uh, inference is one thing that becomes very challenging, and it is rarely rarely the device problem, right? It is actually how bound this problem becomes, memory bandwidth bound this problem becomes, in spite of having a very good hardware or very good GPU for the compute, right? So it's not how fast the GPU can crunch numbers. Instead, it is how brutal. It is a brutal physical limitation. It is overwhelmingly memory bandwidth bound. So the primary offender is the standard KV cache here. So during the text generation, an LLM must remember all of the context it has previously processed and generated. To avoid recalculating this context from scratch at every step, the model caches the key and value tensors for every attention layer. However, for every new token that is generated, the hardware must physically haul this entire continuously growing KV cache from the high memory bandwidth into GPU's SRAM. As the sequence length grows, the actual memory operations, the mathematics that you're going to perform, take a very small part of the whole latency or the whole compute time. But the GPU ends up waiting for that massive cache data to travel from the memory bus to its SRAM. So basically, this is what the GPU state is. It just keeps waiting, keeps waiting, keeps waiting, and finally, when it gets the data, it quickly computes everything and gives it back to the cache again. So basically, GPU ends up staying idle for most of the time, right? So let's actually dive a little bit deeper into what this KV cache is and how this works, and then come back to the code walkthrough sort of again, right? So what happens is, let's assume you are getting an input of length, let's call it X, and the shape is going to be batch size, then sequence length, and dimensionality. Here, let's not get the head dimension for simplicity, right? Also, assume that is equal to 1. So essentially what happens is, give me a minute. Yeah. So essentially what happens is x is going to be sequence length, comma dimension. Let's just call it SL, comma dimension, right? So this x is going to go through W Q projection, W K projection, W V projection, which is going to give us the query key and value, which are going to be the same, SL, comma D, right? So now, what is attention? What is attention? Attention is basically softmax of Q, K transpose plus mask, any sort of mask, and you're going to give it plus square root D and into value, right? So let's first focus on this part and let's compute that. So let's just assume this is going to be Q, which is, let's say, 3 tokens. This is going to be SL, this is going to be D, and you have K transpose, which is 3 tokens again. So this is going to be sequence length, this is going to be D, right? So what you're going to get from here? So basically here, what happens is you're going to get a matrix which is going to be every, let's just write it down, query of I attending T of I, right? So when you do a MACML here, what you're going to get is every query is going to attend key, right? So this is going to be, let's call it J for simplicity. So this is the representation. So this is going to be 2 comma 1, 2 comma 2, 2 comma 3, 3 comma 1, 3 comma 2, 3 comma 3. Okay. So what is going to happen here is, every um, query, right? Every query is going to attend to every key. So 1 is going to attend to 1, 1 is going to attend to 2, 1 is going to attend to 3. Similarly, the second row, which is 2 is going to attend to 1, 2 is going to attend to 2, 2 is going to attend to 3. Similarly, the third one. Now, next thing is going to be the mask. So, as you all know, in causal mask, it is going to be a upper triangular matrix of all negative infinities or a lower triangular matrix of all zeros. In that is what you're going to say. So this is going to be negative infinity, 0, 0, negative infinity, then 0, 0, 0. So what is this suggesting is that every token is allowed to look at itself and the history behind it. It's not allowed to look at the next future tokens, right? So query, or rather the token 0 is only allowed to look at itself. Then token 1 is allowed to look at 0, but it is not allowed to look at the next token, the future token. And the third token is allowed to look at 1 and allowed to look at 0, or rather 2 is allowed to look at 1 and 0, right? So what are you going to get from here? You're going to get 1, 1, negative infinity. So 2, 1, 2, 2, negative infinity, 3, 1, 3, 2, 3, 3, right? So this on top of this, you're going to do the softmax. So here is the softmax. So what is softmax? Softmax is essentially uh, e power the current element divided by all the elements, and this will always return values between 0 and 1. So you can get a token with negative, not negative, 0 probability, but the values are between 0 and 1. So what is going to happen here is this 1.1 or the correlation is going to translate into probability or weights. So how much important is the correlation between the query's first token and the key's first token, right? So this is going to be P11, then zeros, because when you put negative infinity here, this essentially becomes 0, right? Or tends to 0. So you can call it 0. Then P21, P22, 0, P31, P32, P33. So these are the attention scores. These are what we call the attention scores, right? Suppose this, you're going to multiply this with value. So let's just copy this, copy, and we will paste it here. And you're going to do value. So this is going to be G tokens again. This is going to be sequence length, which is going to be D, right? So now the final output that you're going to return from the attention module is, let's just name these, going to be P11 V1, P21 V2, sorry, V1 plus P22 V2, then P31 V1 plus P32 V2 plus P33 V3. So this is the final thing that you're going to return. Now let's extend this thing to the scenario where you have one extra token or one more new token, right? So let's just change the color and figure out what would happen then. Let's take red now. So what would happen now? You're going to add new token, right? After one token, or let's say new token, what's going to happen is you're going to SL plus 1, D, SL plus 1, D, SL plus 1, and D. So you're going to add a new row here, plus 1, going to add a new row here, plus 1, right? Then what happens is, um, once you start attending, or rather the query starts attending the key tensor, this square matrix is going to become a larger square matrix with 4.1, 4.2, 4.3, 4.4, and there's going to be 1.4, 2.4, and 3.4. Mask again is going to be negative infinity, negative infinity, negative infinity, 0, 0, 0, 0. So basically it increases, the square increases by 1 unit. And now because of this, what happens is, uh, because of the mask addition, this this row, right, this or rather this column, or this column without the last row is basically insignificant. So whether you do it or not, it's always going to be added with negative infinities, and it is going to end up as negative infinities. So it is not that significant. However, the last row is going to be significant because that is the representation of a new token or the compute associated with a new token. So this is going to be very important. So we'll have to keep it. So this becomes 4.1, 4.2, 4.3, 4.4, right? So after softmax, it's going to be 4.1, 4.2, 4.3, 4.4, 0, 0, and it's going to be 0. So these are the attention scores, the new attention scores. When it comes here, it's going to be 4-1, P4-2, P4-3. Let's move it a little bit. We need some space. 4-3, P4-4. Then since it is 0, 0, 0, yeah, and we do have one more uh, value which is going to be added here. So this is going to be the V4. So ultimately what is going to happen here is it's going to be P4-1, 1, P4-2, V2, P4-3, V3, P4-4, V4, right? So now if you observe a little carefully, always you're not going to need the whole query, right? Because uh, the query dot product with the key dot with the already existing key dot product is already stored in this inner square, so you don't really need that. And what you do need is you always need the new query token, but you need the whole key token, like the key context and the whole value context, right? Because what you're going to do is every key is going to attend to every token, every new token from the query is going to attend to every key that has already existed before. So you need the whole context with respect to key. So here you're going to cache the keys or the key projections of each and every token. That is what forms the k of the key v cache, and the every new projection is going to be just appended to it. So you're going to have let's say some keys already existing, then whenever this new token comes in, you're going to just append it, and every new query token is going to be handled as a single uh, tensor or single row in the whole matrix, because previous queries are not really required. So once you get the query and you're done attending to all the keys here, you're going to develop this row only, because this is already computed and this is not going to change. And this, as we saw, this part of the tensor is irrelevant, so this really doesn't matter whether you have it or not. So we can just ignore the top part of it, and you're going to consider only the bottom row. After that, you don't really necessarily have to add any mask, because adding zeros doesn't affect it, right? So you can either skip it or have it in your code, doesn't really matter. So finally you're going to get the same thing, and once you pass this through softmax only the row, you're going to get the final row here. These again don't matter because these are not going to change and they are not going to affect the current token in any way, because whatever was affecting is already being considered. So this new row is what you're going to consider. And going further, however, you need the whole value context or the value tensor, because this probability vector or this weight vector is going to go through each and every value and figure out what it needs based on this weight, right? So P41 is going to get multiplied with the first elements of all the value tensors or the value rows and figure out what it wants. So this ultimate row, when multiplied with value, is going to give you this final tensor or final row in the tensor. This, however, doesn't matter because it is not going to change and it is not going to affect your final computation. So whatever you need is here. So what we just did is we basically skipped sorry, we basically skipped all of O of n squared attention computation because it is redundant or doesn't change, right? But this is only possible in the decoder only models, because KV cache doesn't really make sense in encoder models, as you have seen in the previous project where we had used BERT for text generation, right? There we don't really cache KV tensors, because they keep updating after each and every new token. Every new token is allowed to look in the front, in the future, and in the history. So it can change the what you say. It can actually sort of change the states of the past tokens as well, because in encoder based models, the mask doesn't really have any um, job to do apart from removing the padding, right? So the current token can look at the future and change its own state, which is not possible in decoder only models because of this infinities, right? You can't look into the future and then change your own state. So that is why uh, it's the and all of the O of n squared attention is basically redundant and it doesn't change. So all of O of n squared basically translates to O of n computations, because you only have one vector now. Oh, sorry, you only have one vector that you want to multiply with the tens when you want to multiply it with the matrix. So instead of O of n cross n, you are going to multiply only this one vector with all of the n squared tensors in some sense. Not n squared. The operation is O of n. I hope you're getting what I'm trying to say, right? So that is basically how the KV cache works and what you're going to cache. So basically, you're going to cache all of the keys, and whenever a new token comes up, you're going to append the new token's key representation to the already existing history, and you're going to always cache the value as well. And whenever a new value representation of the token comes into picture, you're going to append to already existing history, right? So this is basically the explanation of what KV cache is and how this is helpful. So you're basically trading uh, memory for speed, right? So instead of this becoming O of n squared and O of one memory, you're going to basically move to O of n and O of n. So you're getting speed, but you're getting hit at the memory. So this getting hit at the memory, right? O of n is currently affecting a lot of models, because you need to manage this memory, and this memory really explodes after a point, and that is what we're going to see in this project also, right? So let's just check what we have here, right? So yeah, let's just see what we can figure out from the code also, and if we can get some sense of how much this memory requirement is from the code itself. So what I'm trying to do here is I have batch size 1, but I have maximum sequence length as 4096, and the head dimension is included here because it is in code and we can actually figure out what we want from here. And the number of heads is 16. So let's run this. Hopefully I have selected the correct. I'm using JAX, so we will be running all of the experiments with JAX, right? So the vanilla MHA, which was the first attention variant which was introduced in attention is all you need paper. So we'll see how much memory requirement this variant would need, right? So at sequence length 4096 and head dimension 64 and number of heads being 16, you need around 16 MB of uh, memory to store all of history of all the 4096 tokens. Though this looks small, but when you project it to millions of users and you basically move the context length from 4096 to maybe 128K, right? This number starts exploding. So let's just try with uh, maybe uh, should we try with 128K? Let's try with 128K. Uh, let's run this. Let's try to get this. Yeah. So you saw that, right? It jumped from 16 MB to almost half a GB here. So now if you extrapolate this to multiple millions of users, right? This handling of memory becomes really difficult, and this memory also explodes. So what we have tried to do in this project is we have basically tried to get rid of the two representations. So as we saw, X goes through W Q W K W V. So query is basically asking what am I looking for, right? Key is saying what I can provide, and value is saying what I would actually provide when considered, right? Because value is being used as a weighted to do the weighted sum of the attention scores, right? So value is basically when you are going to use me, what value I'm going to provide to you. Key is basically saying when you are just casually looking at, okay, what can you provide or what can you provide. Uh, Key is saying that, okay, I can provide this. So if you kind of think from the philosophical perspective in one sense, maybe this is kind of similar, right? What I can provide and what I can provide and actually consider me. So you can basically merge both of these into one tensor itself and then train the model, right? So what basically happens is what I have done in this project, as you will see, is X will go through WQ because you need all the query, you'll get query, and X goes through WA, which is going to be A, and the attention will become softmax q into A transpose by square root D plus mask into A again, right? So you have A here, you're going to have A here. Now, uh, what trade-offs do we have here? Yes, there is some effect of losing accuracy here because you're using the same tensor to represent what you're asking the token that it can provide and what it will actually provide when considered, right? But look at the advantages, right? You're going to slash down the memory requirement by approximately 2x. So the scenario where you are saving K and V as separate two tensors, you require 2x more memory when you compare it to the scenario where you're going to save only A tensor itself and you're going to use A tensor only in both places, right? So that is what is group tied attention. So if you also remember, there is something called as GQA where it is called group query attention, where you have lesser number of KV heads per query head, right? So basically the same concept is applied here also. So here for the same config of input, what we are going to get when you are going to use GTA instead of normal MHA. So you are down from 500 MB to just 125 MB, which is already 4x smaller. So you are going to kind of save 4x the memory approximately when you're going to move from normal MHA to GTA, and even slight or not slight, you however going to save still a considerable amount of memory when you're going to move from GQA to GTA. So what happens with that is, or what next are we going to see is how we can reuse this saved memory into making our models more intelligent or more heavy for specific tasks. You need a larger number of parameters and more models and more layers and all of that, right? So we are going to see this next. So now let's move to the blog, and I'm just going to show you the difference between these architectures pictorially sort of. So what happens is in MHA you have query key and value of all 16 heads, and you have KV cache for K and V for all 16 heads, and then you have learned positional embeddings. Uh, when you go to rope implementation, you have query key value 16 heads rotated. K and V is again stored, and you have to store it for all 16 heads, and you have rope as the uh, concept, or rope as the provider of positional information. Then you have GQA, which is 16 query heads, but you have only four key and value heads. So here you're already reducing the head dimensionality of key and query to kind of store lesser or to use lesser memory. But this tied attention and group tied attention take this further. So instead of having two representations, key and value separately, you have only one A, which is having 16 heads, and A also has 16 heads, query also has 16 heads, and you're going to cache only one tensor which is of 16 heads, and here you're going to use ALiBi to provide the positional information rather than positional embeddings or rope. And GTA extends the TA's implementation further, where you have 16 query heads, but you have only four A heads. So A is basically, I'm calling it answer tensor, but you can call something else or anything that works for you. So I'm going to call it answer tensor, and we are going to cache only the A tensor, which is going to be four heads. And again, here you are going to use ALiBi to provide the positional information. Now, why ALiBi and not row? We will come to that later in a point in some time. So basically, this is what happens here, right? In the whole project, A is also behaving as key and A is also behaving as value, right? So that is basically the project that we are having here. Let's just try to see the code also, how we have implemented it. So we are using JAX here, and this is the config. So number of layers are 24. The dimensionality of the model, the internal representation of tokens, how much dimensionality that has is 1024. Num heads is 16 and num kv heads is 4. And this is ALiBi. So what ALiBi is going to do is, I think I do have that representation somewhere. Let me just find it. I think I had talked to Gemini about that. If we can go to Gemini and check. Yeah, let's just go to. I should have it here somewhere. So let me try to find it. Or maybe let's just go to Gemini. Let me open the chat. Yeah, here it is. So yeah, how ALiBi works is, you are going to have query key value, the same attention formula, but uh, the mask here is going to be the positional bias that you're going to introduce, right? So this delta is the relative distance between query and key token, and m is the head specific slope, which is a fixed scalar, and it can be folded into the graph itself when JAX is going to do constant folding. So let's just take an example of the cat sat down, and let's say the fifth token is going to be period. So it looks at the cached keys, which is K1 to K5. Then it's going to compute K and Q and K transpose. Let's assume that it got every token equally likely. Then what distance matrix is going to do is, it is going to give a penalty of negative numbers. So as you know, when you are trying to add negative numbers, you are going to reduce that token's importance, because negative infinity is basically zero importance, right? So you're going to add negative numbers to that specific token, and the magnitude of that number, or magnitude of that negative number, is depending on how far the key token is when you're considering the current value token. So for example, let's assume delta is going to be -4, -3, -2, -1, and 0. So 0 is basically the current token. So now, since you have multiple heads, every head is going to apply this distance matrix by multiplying it with a scalar, and that scalar is basically also called as slope of m. And here, for let's say head 1, it is going to be 0.5. So this 0.5 is going to be multiplied with the distance uh, matrix, and you're going to get the final penalty. And this final penalty is added before you do the softmax. So you're going to scale the importance of the tokens with respect to the distances uh, the query tensor has with respect to the key tensor. So since it is all equally likely and you're going to add these penalties, the final force changes. And ALiBi actually forces the transformer module to uh, attend to or give importance to the nearby tokens only. That is why ALiBi drastically fails when the context is really long, because let's say I have a huge paragraph and I want to get back to the point in the which is at the starting of the paragraph. Since alibi is penalting so much heavily when the information is far away, you basically lose that context. So alibi is not really very good for large context, but in small context task, it is basically a sort of a winner in some cases, or even it comes to very close to the ropes performance in some sense, right? So that is what we have here. I mean, I have used alibi instead of rope in all of the TA or GTA's implementations. So here alibi plus alibi bias and alibi bias for both TA alibi and GTA alibi. So now, why do we want to use alibi and not rope in TA and GTA? So big TA is basically tied attention and GTA is basically group tied attention. What happens is, uh, let's say, what does rope do? So it has Q, K, and V. So it is going to basically rotate the k tensor and the q tensor, and it is going to then do mask computation, mask addition, and it's then going to do softmax. So basically, in rope or in rotatory positional embeddings, the positional information is actually embedded into the projections of the token itself. And how does rope achieve that? By rotating these tensors. But now, as you might remember, in this project, we are going to use a tensor which is going to behave as query and key tensors, query and value tensors, right? So let's say you rotate a tensor when it is behaving as key, you end up actually rotating the value tensor also, where a is behaving as value. So this rotation of value tensor is not really helpful, and it's actually uh, not. It's actually bad when you put in a positional information in the value tensor, because value tensor is basically uh, value tensor is going to give you all the value tensors and ask you to do a weighted sum and choose which values you want to give more information more weight to, right? Imagine you add positional information there, it is going to ruin your weighted sum, and you end up choosing the tokens that you are not supposed to choose in some cases. So this is where rotation sort of became my enemy, and I didn't want to use rope uh, because it was rotating both the tensors simultaneously. So that is why I went with alibi, where where you're going to add the mask and you're not going to touch any of these values. So basically, it helped me to keep the matrix projections intact, and use them as it is wherever I want them, wherever I wanted to use them, right? So this is why ALiBi came to my rescue, and it helped me achieve whatever I tried to achieve in this project. But the original GTA paper, right, the original group tied attention paper, actually circumvented this issue by implementing a complex partial rope strategy. So what they did is they took a single head projection, they applied rope to it, they broadcasted it across all the groups, and then concatenated it with the unrotated half of the tied tensor to form the final key. So I didn't want to go into this complexity at this point. I wanted to keep the implementation as simple as possible, and that is why I have chosen ALiBi, right? So it kind of becomes messy at places where you have to slice the tensor, rotate half of it, then concatenate half of it with the other unrotated tensor and all of that. So I didn't really want to go down that path, and I just abandoned rope completely and chose ALiBi over it. So that is where ALiBi comes into picture. And let's just see if I have something with ALiBi also. Yeah, I do have the explanation here, right? So if we use a single tight tensor A, we cannot use the standard rope or rotatory positional embeddings because it physically transforms the vector based on its position. And if you rotate the tensor to act as key, you destroy the geometric value or the geometric meaning of the value tensor. So what we have done here is we are going to apply, or we are going to add the positional information, add, not change. You're going to add the positional information to the already existing scores, and then you're going to take the softmax. So what basically happens here is that you're going to end up with some more memory because you're going to create this positional information, and you're adding it somewhere, right? So basically that's why some additional memory is taken up, where here as you can see it is going to take 1.95 MB, and that will most likely stay constant, right? Because your positional information size is not going to change with uh, context of sorts. So even though the content of the context changes, how much you're going to penalize the far away tokens with respect to or compared to the near tokens is always going to stay the same. So this we can just create it once and cache it forever and use it whenever we are going to compute the attention. So basically that's why I have chosen ALiBi. And now let's walk through a little bit on how I've benchmarked this and how I've trained it also. Let's first go through benchmark. So here we are going to create empty caches because we do require KV cache, and that KV cache basically depends on each and every variant and how we are going to use them. So if it is going to be tied attention, we are going to have only batch size, num heads, max length, and depth. But if it is going to be GTA, where you have lower number of KV heads, it is going to be batch size, num KV heads, max length, and depth. Whereas if it is going to be GQA, you're going to have two caches where it is going to be K is going to be cached separately, and value is going to be cached separately. And so is with vanilla also. The difference between GQ and MHA is that here you're going to use the full range of heads that query has. Here you're going to use lower number of heads. So that is what we have here, and I have all the implementations in operators.py where we have tied attention, where you have only WQ and WA, and when you are going to use the cache, you're going to dynamically update it. So just a simple explanation of what this is, right? What happens is whenever you're implementing this dynamic update in any of these frameworks, right? Uh, since GPUs or any hardware for that matter, they are fixed, right? They have some slots like this which are fixed, and they always like things to be in power of 2. So in case of LLMs, what happens is you have a sequence length, and since it is auto-regressive, you keep adding stuff to the same tensor again and again and dynamically change its shape. GPUs don't really like it. So what we do is, what this dynamic slice does is, you basically figure out what is the maximum context length or the maximum length you're going to run this model for, and you're going to assign a massive chunk of memory just for the cache. So after the first prefill, or rather after the first token is generated, what you do, you are going to fill up this part of the cache with the prefill context, and each and after each and every token is generated, you're just going to fill one slice like this. So what advantage this gives is, uh, what happens is when you are having a massive cache here, this basically becomes a contiguous cache. But whenever you want to kind of append to it, or let's say keep the information that you want to access to get access together close by, that becomes kind of difficult in these scenarios. So what happens is, let's say only this much space is available after whatever contiguous chunk you have allotted. After certain tokens have been assigned, this space doesn't become contiguous after some time. And as you know, memory access, if it is contiguous, or memory if it is contiguous, it is extremely good, so that you can take advantage of the locality and pull everything that is present in nearby locality, right? So this, to avoid this sort of problems, what you do is you basically assign a large chunk of memory outright at the start, to accommodate all of the new tokens that are going to generate, and you're going to fill this uh, memory itself token by token once you start generating all these tokens. So that is what this dynamic update slice is going to do. It is going to take in the already existing large memory that you have assigned to it, and it is going to append the new A part by part, or token by token. So yeah, that is what we have here. And then we have the ALiBi uh, input, the positional input that we have. Then you have matmul. It should also be somewhere here. Let me just find it, the Q and K matmul. Hold on. Yeah, it is here only. The Q and K matmul is here. Then to this scaled attention logic, so going to add slopes and the distance penalty. Then if it is having a causal mask, it should have a causal mask. So that is what you're going to be multiplying here, or rather adding here. There is no multiplication of mask. It is going to be always addition of mask. And after that, you're going to do a softmax, and then have sort of added a dropout here. And after that, you're going to again multiply a, which is behaving as value here. So that is tight attention. And tight attention with positional embeddings is also present, where instead of ALiBi addition, you are going to just add the uh, positional information as positional embeddings. So let me just find it. I think I have it here only somewhere. Should have it here. Uh, so this is the cache. Oh, I'm not able to find it. Okay, I think this is the mask here only. Yeah, yeah. So this is where the positional information is also added, or is it? Okay, actually, okay, I remember now. I think in benchmark.py or train.py you'll find it. Is it here? Okay, I think it is in cause. Yeah. So if it is normal MHA or if it is any variant of attention that is going to use positional encoding, it is going to create a positional embedding matrix and you're just going to add it to the input itself. So again, in rope and in positional embedding concept, you're always going to mutate the already existing tensors, but in ALiBi you don't. So in ALiBi, it's actually more of addition. It's more of addition of information of the position information rather than mutating the tensor itself, right? So operator.py has implementation of all of the attention variants that I explained or this project is going to do. So let's just go through them quickly once. So we saw tied attention positional encoding, which is basically same as tied attention, but you have positional information being uh, kind of alloyed in the tensor itself. You're going to mutate the input tensor. Then group tied attention is basically the same thing, but here you are going to have lesser number of KV heads, and that is why when you're actually doing the matmal, you're going to kind of expand it, right? So this is where this comes into picture. So JNP broadcast 2, what this does is it actually doesn't change the underlying memory organization of the tensor. It basically just edits the metadata uh, of size and strides so that it can behave as a bigger tensor than it is actually doing, than it is actually having, or than it is actually be, or whatever, right? So what actually happens is, let's say you have a tensor of um, size, let's say 2, 3, and 4, and you want the tensor to be 2, 3, 4, 3, and 4. So what happens is inside the memory arrangement or inside the tensor, the memory layout is going to be contiguous. So inside the memory, this tensor is arranged like this linearly, and you're going to how do you access all of the elements? They are basically done using stride. So if this is the size of the tensor, stride of the tensor is going to be 1, then it is going to be 12, I assume, and then it is going to be, no, this is going to be 4, and this is going to be 6. So this is the strides. These are the strides. So what this basically says is, whenever you are in the last axis, how much elements you need to jump to move to the next element. So you need to jump only one element. But whenever you are in the second dimension, how many elements you have to jump linearly to move to the next element in that dimension. So you'll have to jump 4 elements to move to the next element in the dimension 2, right? Then coming to the last dimension, whenever you are in the final dimension, how many elements you have to jump to move to the next element whenever you are in the current dimension. So whenever you are in the third dimension, you have to jump 6 elements to move to the second element whenever you are in the first element in that dimension. So strides are basically used to explain or tell you how to move when you want to access all the elements. So now when you're actually trying to broadcast it, you basically say that, hey, I don't actually have these many number of elements, right? I don't have um, four 2D matrices to accommodate, or I accommodate only two 3D matrices. So whenever you are done accessing both the elements in the final dimension, move the pointer back to the original zeroth element and then do a two element jump sort of. So whenever you are in the last dimension, what you do is you basically do, so this is the index, not batch size, and then you do, then once you finish this, whenever you're going to, let's say, the second position in the third dimension from the right side, you're going to go back to 0 again, and you're going to back to 1 again. So basically this looping of the same batch is being accessed whenever you're going to broadcast it to a higher dimension is done by this JNP broadcast to. So you're basically not uh, creating more memory. You're basically having the same memory, but you're going to change the access patterns of that memory using strides. So that is what we are using in this group tied attention, so that we don't end up creating more memory, and which basically defeats the whole purpose of tied attention and group tied attention, right? So that is what we have here. Then we have the same implementation with positional encodings and not ALiBi. Then you have GQA. Again, you in GQA you have actually three projections, and here also we are using the dynamic update slice, which is what is doing as I explained before. And we also have GNP broadcast to here, and all of the attention basically remains the same. And similarly, we have grouped query attention with ALiBi also. So ALiBi basically fixes with anything because it is an additive information and not a mutating information, right? So all of these variants we have here: multi-head attention, the original attention which was introduced before, the first attention variant. With positional embeddings was the previous one, with rope is this one, and we also have with ALiBi here, and basically all of these. And here is the initialization of all the models, and you finally return this. And all of these are called within this causal LM, where uh, mutating of information is being done. So this sort of acts as a wrapper to all of the previous implementations that we saw, previous attention variant implementations that we saw, right? So now um, this is this is the whole project. Basically, I have benchmarked all of the attention implementations that I had implemented, and I'd also trained all of these attention variants that I've implemented, because even if the performance is very good, it is not worth it if the accuracy is not really up to the mark, right? So let's just have a look at the results as well. So let's go to the results. Yeah. So can I zoom in a little bit? No, I can't. Let me try to open it in VS Code itself. Yeah. So this is the one. So here we have baseline comparison. This is peak VRAM on the x-axis, and on the y-axis we have basically sequence length repeating. And I have vanilla MHA as the first one, GQA plus rope as the second one, tied attention plus ALiBi as the third one, group tied attention as and ALiBi as the fourth one, and MHA plus rope as the fifth one. So as you can see, uh, MHA, vanilla MHA is taking a lot of VRAM, and even vanilla MHA plus rope is taking a lot of VRAM, but at sequence length 4096. But if you compare the same thing with GQA and group tied attention, right, they are taking significantly lesser. So group tied attention is sort of winning here at 4096 to 4096 sequence length, and it is consuming 2107 MB of VRAM, whereas others are taking more than what this takes up. However, it doesn't really end up winning in each and every scenario, because if you see here, GQA plus rope is taking 1117 MB at length 2048 tokens, and this GTA plus ALiBi ends up taking 1148. So that is the VRAM comparison. Then we have time to first token also. Time to first token basically is how much the attention variant is taking for prefill, how much time it is taking for prefill to consume all of the context that it has been provided. Basically, your query that you have provided to the model. So here as well, GQA plus rope ends up as the winner, and GTA plus LLI is not far away as well, but also MHA plus rope is not also far away. But vanilla MHA is taking significantly higher amount of time for producing the first token. But this is where GTA plus LLI completely destroys all of the competition. Where TPOT basically, how much time do you take to generate each and every token on an average up till whatever token, whatever context length you have. So across all of the sequence lengths, GTA plus ALiBi takes the lowest time to produce uh, the next set of tokens after producing the first token. So basically, this is how it is performing. Now, this was how it is performing purely on random numbers, right? So let's actually even check how it how it performs accurately in the next block. There are few more uh, comparisons that we can do. So as I had already mentioned to you that uh, whatever amount that we are saving here, right? So here, let's say we had 500 MB, and with this attention variant, we are going to just use uh, fractional part of the memory that is available, or rather, fractional part of memory of the whole memory that is available to us. So, can we have the same size of the model and try to sort of utilize whatever memory we have saved and re-implement or reuse all of that into making the models deeper and probably increase the number of parameters also, because when you make the model deeper, the number of parameters always increases, right? So with that, what happens is, let's talk about this. Let me open this also as VS Code if possible. Is this the one or is this the one? Yeah, it was this. So what we are doing here is, it is the depth narrative now. We are going to compare the 24 layer baselines with the GTA 30 layers, because we are saving a lot of memory in GTA, right? So the first one is vanilla MHA 24 layers. Then we have MHA plus rope, which is 30 layers, just for 30 layer comparison. Then we have GQA plus rope, which is at 24 layers. Then we have GQA plus rope at 30 layers. But as you can see, TPOT is still better with higher number of layers. But because we are saving a lot of memory, that memory transfer of the entire KV cache is lesser here. That is why we are getting tokens faster in case of GQA plus rope. And here also GTA sort of beats everyone while being a deeper model. So GTA plus LLI at 30 layers with approximately 374 million parameters, it is beating all the variants in spite of being deeper in TPOT at all the sequence lengths. Similarly, if we consider VRAM, it is taking lesser when you compare to MHA plus rope and normal MHA. And even if you compare to GQA plus rope with 24 layers and with 30 layers, it is sort of matching here. So VRAM we have already saved. We are not able to save much, but we are able to save some bits of VRAM as well. So again here, this is time to first token where GQA plus rope of 24 layers is actually beating everyone, which is obvious because the model is itself small. Uh, Similarly, GQA plus rope here and GTA plus ALiBi is how they perform here. I'm not sure. Let's just look at this also. So what we are doing here, what we are doing here is, yeah, what we're doing here is we are fixing a parameter budget of approximately 354 million parameters, and then we are seeing what we can do. So here we are comparing vanilla MHA 24 layers, which is 354 million parameters, Then we have MHA plus rope, which is 353 million parameters. And then we have GQA plus rope, which is 359 million parameters. And then we have GTA plus LLM, which is 28 layers, but it is still 352 parameters. And again, as you can see, TPOT is lesser for GTA when you compare to any other variant. And you can have a look at this also. Peak VRAM is also lesser when you compare GTA 28 layers and like more number of layers but still less VRAM, and lesser number of layers but still more VRAM. So this is basically what we have in the whole project. And let me just do a quick check. Right. So we are back here, and we have already discussed the variants of all the attention implementations that we have, and we have seen how all of the variants perform on random numbers. So let's actually check if those implementations are accurate or not. So what I have done as part two of the same project is that I've kind of trained 29 variants, because there were 29 variants of the attention, and checked their memory, their timings, their accuracy, and all of that is mentioned in this blog. So let's go through this. So what we have done here is what is the best way to compress attention, manage KV cache, and encode the sequence positions when the hardware budget is strictly constrained? So instead of running isolated tests, what I had done is I had built a custom JAX Flax pipeline and executed this massive 29 uh, 29 experiments with attention, and it was a full sweep. I did not kind of uh, miss anything and make speculations out of it. All the variants were trained properly, and we have compared it with each other. So what we are wearing in these implementations is the attention mechanism itself, where we use vanilla multi-head attention, the MHA, the group query attention, which is called GQA, tied attention, the TA, and the GTA, which is called group tied attention. And all of these attention variants are supplemented with uh, different concepts or different algorithms of how you provide the positional information, like learned positional embeddings, rotatory positional embeddings, and attention with linear biases, which is ALiBi. Whatever VRAM we are saving, I am reinvesting that into the models again to increase their depth, and hoping that this increase in depth also makes the models more intelligent, right? So that is what we have. So to isolate any sort of bias, what I've done is I have trained all of the 29 models on exactly one epoch of this Wikitext 103 dataset, and I have kept the sequence length of, or the training sequence length, as 512 tokens. Then I have measured the peak VRAM, time to first token, time per output token, across the context lengths of 512, 1024, 2048, 4096. So what we have here is we have, let me just read it out, right? So who won? After passing 7,254 optimizer steps of training dynamics and thousands of inference profiling loops, the data revealed that there isn't just one undisputed champion. Instead, two distinct architectures form the ultimate Pareto frontier for edge hardware. One is grouped query attention (GQA) with ALiBi, and and its contender is group tied attention (GTA) with ALiBi. So if you look at intelligence purely, GQA plus ALiBi 24 layers takes the crown. It finishes training at an impressive validation perplexity of 39.11 at 7254 steps, while the hyper-compressed GTA plus ALiBi of 24 layers finishes slightly behind it, and it drops by around 1.5 points, which is 40.51 validation perplexity. But if you consider edge computing where the memory is constrained, and if you consume as less memory as possible, it is always good. So if that is the constraint, GTA becomes the ultimate survivor. At 4096 token context, the 24-layer GPU plus LLM model requires 2219.15 MB of peak VRAM and decodes at around 0.0056 seconds per token. The 24-layer GTA ALiBi model compresses that down to 2106.90 MB of VRAM and a 0.0053 seconds per token. Together, these two architectures provide the blueprint for edge AI, right? So whenever you want to have deeper models on edge devices like mobiles or smartwatches, you can actually compress the attention itself and reinvest that saved parameters and VRAM into making the model a little bit deeper. So that is what this data and this project is sort of proving, right? So what is happening here is that this is, I mean, I think you can just read through the blog and go through all the images. So I will take you to uh, the place, ultimate place. I think I have results here somewhere. Yeah, so this is what we wanted to look at. So we have alibi variants which are depicted by blue circles, rope variants with golden squares, and learned uh, positional embedding variants with red triangles. And this is basically a y-axis is basically perplexity, lower the better, and peak incremental VRAM is here. Here also lower the better. So this is the green box or the green rectangle where VRAM is not consumed as much. And here, if you see, the ultimate winner is the GTA plus LLI of 24 layers with around 40, I think, validation perplexity, and it takes very less memory also. Even though if you see GTA plus positional embeddings of 24 layers takes even lesser memory, but it is not really accurate. So you want to have a sweet spot, right, where you have accurate model also, but you consume less VRAM as well. So that is where GTA plus LLI with 24 layers comes into picture, right? So this is what I had. I think I explained the inference uh, script or the inference project in a deeper way, because I think that is what kickstarted this whole project, and all of the concepts involved in training or inference with respect to the model is same. So basically, in training, what we have done is we have removed the inference part and we have put the training part. That's the whole thing. The operators.py file remains the same. The attention implementation remains the same. So it's just that we have two blocks because I did a lot more data collection and analysis when I trained the models, right? All of these plots were collected after the training. So that is why there are two blogs. Otherwise, one blog itself would have become a very lengthy one, right? So yeah, this is what we currently have, and I think I do have a comparison of reinvestment of whatever we are saving by compressing the attention also, right? So here, if you see, it is all compared between group timed attention, and group query attention. So this is the validation perplexity, again lower the better. And on the x-axis we have time per output token, again lower the better. This is basically saying how fast the model generates the next set of tokens, right? So here, if you see, the best model is I think GQA plus LLI, which is 24 layers, the sweet spot, right? So it is it has the absolute lowest sort of validation perplexity, and it has a tie also here somewhere at with this, right? GQA plus LLI of 28 layers, but heavier models take some more time to produce when you compare it with their smaller counterparts. The absolute best model with respect to time is GTA plus ALiBi, which has 24 layers, and it is having a tie with GTA plus ALiBi at 28 layers. But these take a little bit or rather they take a little bit lesser time when you compare it to GPA plus ALiBi, but they are not as accurate as GPA plus ALiBi. So there is a jump of 1.5 points in perplexity, and they are slightly more confused in some sense when you compare it with GPA plus ALiBi. Plus, but this map sort of explains where these models are placed, right, and which model you should take based on your system requirements or the constraints that you have. So yeah, I think that is what we have here. Let me just check if I have one more picture, or is that what we had? I think that is what we had. Yes, maybe just one more picture. Yeah, this one looks interesting, right? Yeah. So this is basically the depiction of ISO KV cache. So what I'm doing here is based on the absolute number of megabytes or MB that is consumed with respect to VRAM. That is what we have here. So we have tried to kept the amount of VRAM consumed in MB as similar or as close as possible. So on the left hand side of y-axis, or the left hand side y-axis, is basically peak VRAM in MB, and on the right hand side it's validation perplexity. Lower is the better. So in both cases, the model which has the lowest bars of both is the best model. So if you compare here, right? So this is the baseline basically, where you have 6 layers of MHA, and it takes 2102 MB of VRAM, and it has perplexity of 54. But when you try to save and compress the attention there, and you reinvest it into the layers with layers extending up to 24 also, you approximately get the same VRAM consumption, but the perplexity drops from 54 to 40.5, which is a huge gain. Similarly, GQA is also present here, where the same reinvestment helps, and it is taking slightly more memory than GTA and MHA, but perplexity again is much better when you compare to the 6 layers MHA with ISO KV cache. So yeah, I think that is what I had to present in this project. So the whole code is open source, and you can go to my GitHub and check this out. Also, this is not the ultimate solution or a map that I'm trying to present. This was just a sort of effort, or honest try from my side to study all of these variants and present it in a better way after training it on actual constraint hardware. So I have trained all of these variants on my laptop itself with 8 GB VRAM, and I think the specs also I have mentioned here somewhere. I don't know. It's I think, okay. Let's just check what hardware I have. I have only forgotten, which is great. Uh, do I have it here? Get it? Yeah. So I have RTX 5050 and it has 8 GB VRAM. So yeah, it is an actually constrained environment. I don't have massive GPUs to train these variants on, right? But however, as a disclaimer, or as a honesty from an honest perspective, this is what I have. Let me just read it out. If you want to, I mean, whenever you read the blog, you'll actually read it. So before declaring this the ultimate solution for LLM inference, it is important to practice good scientific hygiene and acknowledge the limitations of this study. Scale and parameter count. So these experiments were run at a relatively smaller scale, roughly 350 parameters for 24-layer models. While GTA works beautifully here, production grade frontier models like Mistral or Llama 3 rely on massive scaling laws, where standard GQA plus rope currently rules the supreme. rules as the supreme. So the dynamics of tight attention at 7 billion or 70 billion parameter scale remain an open question. Compute constraints and seed noise. Because I don't have a massive H100 cluster sitting in my living room, these 29 architectures were trained for a single epoch, 7,254 steps on a single random seed. The perplexity gaps between the top contenders, example 39.11 versus 40.51, are really tight enough that they could be possibly be influenced by run to run noise as well. So that is one thing which I could not figure out what to do about, but that is what I had faced, and that is what I'm presenting here. Perplexity versus downstream generation. Throughout this post, I used validation perplexity as the proxy for model intelligence. However, a lower perplexity score does not always perfectly translate to coherent long form text generation or complex downstream reasoning tasks. So there are many more metrics that you can use to actually see how this model is trained and how it is actually performing. For me, I had used validation perplexity as the metric to see how intelligent the model was, but that is not the only way to judge the models, right? That being said, while the training metrics, that is perplexity, carry these caveats, the harder profiling metrics, that is VRAM scaling and TPOT, are deterministic because they don't actually depend on the trained models, right? You can actually run and get these metrics even on random numbers without even training the model. It actually depends on the architecture of the model and not really the uh, trained part of the architecture, right, or the model. So the mathematical reality of shrinking the cache footprint by 4x per layer and the resulting speed up from increased arithmetic intensity remains a definitive hardware win. Yes, so this architecture is definitely a very good architecture where you can actually compress the attention but still not affect your accuracy. But yeah, there are many open questions here, and let's see if I can try to get some more projects and answer them. So yeah, finally, like Chandler Bing does statistical analysis and data reconfiguration. I work on machine learning and deep learning. If you like this work, do check out my other repositories on my GitHub, and you can connect with me here on LinkedIn. So I have my LinkedIn profile posted here. So yeah, I think that was it for this project. Thank you so much for watching, and let me know what you think about this project and anything else that you want to discuss. Bye bye.